Good morning, everyone. We, the Department of Computer Science and Engineering, presents Engineering Mathematics 4 mini project series with nonlinear programming, unconstrained optimization. Our team consists of Saurabh Pandey, Sachin Nisar, Janvi Panchal, Siddhi Dubey, and Sarthak B, under the guidance of Supervisor Dr. Teena Trivedi. So the flow of our presentation would be introduction given by Sarthak B, 1D search method by Siddhi Dubey, golden search method by Janvi Panchal, Newton's method by Saurabh Pandey, and gradient search method by Sachin Nisar.
Introduction. A direct search method for nonlinear optimization problems with nonlinear equality constraints is presented. A filter-based approach is used which allows infeasible starting points. The constraints are assumed to be continuously differentiable and approximations to the constraint gradients are used. For simplicity, it is assumed that active constraint normals are linearly independent at all points of interest on the boundary of the feasible region. An infinite sequence equate is generated, some of which are surrounded by sets of points called bent frames. An infinite subsequence of these equates is identified, and its convergence properties are studied by applying Clark's non-smooth calculus to bent frames. It is shown that each cluster point of this subsequence is Karu's contractor point of optimization problem under mild conditions, which includes strict differentiability of objective function at each cluster point. This permits the objective function to be non-smooth, infinite, or undefined away from these cluster points, and the objective function is only locally ellipses at these cluster points. It is shown that certain directions still have interesting properties at these cluster points. Thank you.
My name is Siddhi Dubey, roll number 18, and my topic is one-dimensional search. So if we remember that in linear programming, we would basically have linear function, for example, f of x equal to ax plus b, and we want to minimize or maximize it. And we know various methods to solve the same. But now this is no longer a linear function. So let's take example of x minus 1 into x minus 3. So we will basically maximize it, and when we expand it, it's going to be quadratic. And it will be non-linear because we have power greater than 1. So if we want to find the minimum of a function which essentially comes out as stationary point, but if not, then let's see this curve. If we find the gradient of it a gradient is what the tangent line is doing. As we can see in the left side of the tangent line is the tangent line is negative. And as we go on over right hand side, it's positive. So basically we are going from negative to positive. Also while traveling, we can see the negative gradient is becoming less steep. So how do we find the gradient of a function? We just have to differentiate it. So let's expand the function, and we get x square minus 4x plus 3. And as we know, the stationary point is going to occur where the gradient is equal to 0. So when we differentiate the x square minus 4x plus 3, it's going to be 2x minus 4. And when we set it equal to 0, it must be gradient. So as the minimum is going to occur at the point, hence 2x is equal to 4 and x will be equal to 2. So the minimum will occur at x equal to 2. But how do we know if it's a maximum? Well, we have to look at the type of the nature of a stationary point. Hence we find the second derivative because of its gradient of the gradient. So if we draw our quadratic function again, moving from left to right at each point, as we move to downwards, gradient is going to be less negative in left side, and the same as we move from left to right, that is gradient is getting more positive. Therefore the rate of the change of gradient that is double derivative should be more positive. So if we find the second derivative, then it's going to tell us what stationary point is doing. The second derivative is going to be 2, which is positive, greater than 0, hence its maximum. As if the double derivative would be negative, then it's maximum. And if it's equal to 0, it's not determined at this point, but it might be point of inflection. And the last point we will discuss is local and global maximum. Next slide, please. We know if something is local, then it's close to you, and if it's global, then it's kind of worldwide. So if we have a function like this, we will get minimum over here, and the maximum. We will get minimum over here and would be described as a local minimum. But if it's the maximum of the values which are close to that in the kind of range of that function, and this one will be the global minimum because it's the lowest point of the function. The next topic will be explained by Janvi.
I'm Janvi Pansal, serial number 73, and I'm going to talk about golden search method. So this method is applicable for finding out optimal solution for one-dimensional non-linear programming problem. Now, golden section method is a method like other searching technique. We are eliminating the given region, given interval of uncertainty iteratively. This method totally depends on one ratio that is called the golden ratio. So let us start the golden section method. Since this is the iterative process, again, our task is to learn the whole process of the iteration, but everything depends on one thing that is called the golden ratio. And this is by convention, we are writing the golden ratio with gamma. Now, as you can see, the value is almost same as 1.618. So the golden ratio again here is little dependent on Fibonacci numbers. As we know in the Fibonacci numbers, Fn is equals to Fn minus 1 plus Fn minus 2. Fn minus 2, that is any Fibonacci number is sum of the previous two Fibonacci numbers in the sequence. Then from here, if we just divide both the sides with Fn minus 1, we will get Fn upon Fn minus 1 equals to 1 plus Fn minus 2 upon Fn minus 1. That is, gamma is equals to limit n tends to infinity of Fn upon Fn minus 1 equals to limit n tends to infinity Fn minus 1 upon Fn minus 2 equals to limit n tends to infinity Fn minus j upon Fn minus j minus 1. That is nothing but equal to gamma is equals to 1 plus 1 upon gamma, which will give gamma square minus gamma minus 1 equal to 0, which is the polynomial of degree 2. That means it will give 2 roots. So the root would be equal to 1 plus minus root 5 by 2. Now if we consider only the positive value of the root, we will get the value similar to 0.618. Person, next slide please. So now let us start our iteration process. Now in the step 1, it is only given the initial interval of uncertainty. Number of experiment is not needed for us. That is why we will start with our process from initial level of uncertainty L0. That is from, let us consider it from A to B. In the step 2, we will consider two experiments, x1 and x2, within A to B in such a way that it is L2 star distance upper from both the ends. Value of L2 star is equals to 1 upon gamma square L0. That is, L2 star is equals to limit n tends to infinity Fn minus 2 upon Fn L0 equals to limit n tends to infinity Fn minus 2 upon Fn minus 1 into Fn minus 2 upon Fn L0. Now, our task is to generate the value of x1 and x2. That is, x1 equals to a plus L2 star and x2 equals to b minus L2 star. And here we will find out the functional value fx1 and fx2. And if we see that fx1 is lesser than fx2 for minimization problem, we will discard the interval x2 to b. Since the function is unimodal, the maximum value cannot lie here because it is having only one maxima in this function. That is why the function could be like this, in this way. Then in that case, we will discard the other part, that is from A to x1. Now once we are reducing the interval, my next interval of uncertainty would be either from A to x2 or from x1 to b. Next slide please. In the step 3, we will have the new interval of uncertainty. It would be either from A to x2 or from x1 to b. So my next objective is to find out A to x2 and between x1 is there. Now again we will find out another approximation. We will do another experiment which will lie within the point A to x2 in the first case. Now we have to find out L3 star. So L3 star would be equal to 1 upon gamma cube L0 limit n tends to infinity Fn minus 3 upon Fn L0 is equals to limit n tends to infinity fn minus 3 upon fn minus 2 into fn minus 2 upon fn minus 1 into fn minus 1 upon fn n. Now here we are considering the value of gamma to be 0.618. So in the step 4, we will get the next interval of uncertainty, that is L3, and value of L3 would be equal to L2 minus L3 star. That is equals to limit n tends to infinity fn minus 2 upon fn L naught equals to 1 upon gamma square L naught. Now that is why in general we can say that to generate the jth experiment we are doing large number of experiments. Now if we do large number of experiments, that means we are approaching to the optimal solution in a better way. Rather, we are giving interval of uncertainty with smaller and smaller width, and that is more desirable to us. Now that is why to generate the jth experiment, we can generate the formula for the iteration as Lc star equal to 1 by gamma to the power j L naught, and the jth value of uncertainty would be equal to 1 by gamma to the power j minus 1 L naught. That is it. So the next topic would be explained by Saurabh Pandey.
Hello everyone, my name is Saurabh Pandey and my serial number is 80. So the Newton methods. The steepest descent method uses only first derivatives in the selecting a suitable search direction. Okay, and the Newton's method, sometimes also known as Newton-Raphson method, uses first and second derivatives and indeed perform better. So given a starting point, construct a quadratic approximation to the objective function that matches the first and second derivative values at that point. We then minimize the approximate, that is the quadratic function, instead of the original objective function. The minimizer of the approximate function is used at the starting point in the next step and repeat the procedure iteratively. Next. Newton method works well if second derivative of function is greater than 0 everywhere. However, if function second of derivative of the function is less than 0 for some that is negative, so for some x that Newton's method may fail to converge to the minimizer. Newton's method can also be viewed as a way to derive the first derivative of function to 0. If we set g of x is equal to f dash x, then we obtain x raised to k plus 1 is equals to x raised to k minus g of x raised to k and g upon g dash of x raised to k. So there are two graphs shows when Newton-Raphson is for second derivative is less than 0. Next. So these are the steps or algorithm to solve the problem using Newton-Raphson. So step 1, we need to find a point that is a and b such that a is less than b and f of a into f, like the function product of f on a and f of b should be less than 0. Then take an interval from a to b and find the next value, that is x0, that is a plus b by 2. So we are taking the average of the value select. Then find f of x naught and f of dash of x naught, and we consider it as first iteration. Then x1 is equals to x naught minus f of x naught upon f dash of x naught. So from the next so x1 is the value of the first iteration. If f of x1 is equals to 0, then x1 is an exact root, else x0 is equals to x1. Then repeat step 2 and 4 until f of xi is equals to 0, or mod of f of xi is not is less than equal to accuracy. That means we need to repeat the iteration. So let's take an example of the Newton-Raphson method. So the first example, that is f of x is equals to x cube minus x minus 1. So we need to solve this using Newton-Raphson. So let's denote it as a function and we'll take the first derivative of it. So the first derivative is like 3x raised to x square minus 1. Then here on the table, we plot it on the table, that is x and corresponding to f of x. So when x is 0, f of x is minus 1. When x is 1, f of x is minus 1. And when x is 2, f of x is minus like 5. So here are the roots. Our root lies between 1 to 2. So we take x naught is equals to 1 plus 2 by 2. That is, we get the value of x naught. So we according applying to formula, we take the first iteration, that is x1 is equals to x naught minus f of x naught upon f dash x naught. So the first iteration value comes up to 1.34783. Next, and we perform the second iteration then. So repeat using the same until we get it the value close to accuracy. So we perform the second iteration and we perform the third iteration too. So the second iteration gives the value as 1.3252, and then we go on the third iteration. So we continue the same, like x3 is equals to x2 minus f of x2 and f dash of x2, which gives us the value of 1.32472. We need to take the fourth iteration of this sum. Next, so when we take the fourth iteration, we get the value exact same uh, to the third iteration. So we can say that approximate root of the equation is 1.32472. So we need to carry on this exam, perform the solving part until we get the two iterations same. So here's the table of the previous sum, and we can see on the table that last two values of the iteration were same. So we get it as a solution. Next, the further part will be discussed by Sachin sir.
I am Sachin sir, roll number 68. I will be continuing with gradient search method. A number of gradient search methods are uh, based on various gradient methods. These are available for solving constrained and unconstrained nonlinear optimization problems. Common characteristics of these methods is that they employ a numerical technique to calculate a direction in n space in which to search for a better estimate of optimum solution to a nonlinear problem. This search direction relies on the estimation of value of gradient of objective function at a given point. Gradient-based methods are used to solve nonlinear constraint or unconstrained problems where other techniques are not feasible, do not yield desired information about the problem geometry. Gradient-based methods have advantages that they are applicable to broader class of problems than LP, and they provide much more information about problem geometry. They have the disadvantage that they are computationally complex and costly, and they are much more mathematically sophisticated and difficult than LP, linear programming. The most commonly used gradient techniques are steepest ascent, or for constraint problems, steepest feasible ascent, uh, conjugate gradient, reduced gradient. Uh, each of these methods can be found in commercially available mathematical programming software. The method of steepest ascent is mathematically simple and easy to program, but converges to an optimal solution only slowly. On the other hand of spectrum is reduced gradient method, which has a higher rate of convergence but is more mathematically complex and difficult to program. Before presenting an example of method of steepest feasible extent, we must develop some terminology. Define the gradient of a function f of x to be vector of first partial derivative of the function. The value of f at point P naught, where P naught is an n tuple equal to x1 naught, x2 naught up to xn naught, which is a vector called as Vp naught, which with entries equal to the vector Vp naught. The direction in space of steepest ascent from the point P naught, direction in which the rate of increase is objective function f is maximum. Let's take an example. Taking a unit vector Vp naught to be V of P of 0, calculated as Vp 0 can be determined as uh, the vector Vp0 and its determinant. which will be gradient vector. Considering the following optimization problem, we need to find the maximum possible value of function f of x1 and x2. Here we are taking multivariate function so that we can understand it better. The function is 7x1 4x2 plus x1 into x2 minus x1 square minus x2 square, which on simplifying gives us 2 by 3 x1 plus x2, which will be less than or equal to 8, minus 5 by 12 x1 plus x2 is less than 2, which gives us x2 is less than equal to 4 for x1 and x2 greater than or equal to 0. To begin evaluate an expression for the gradient. We will be evaluating the expression of the gradient by partially deriving the function with x1 and x2 separately. That will be giving us 7 plus x2 minus 2x1 and 4 plus x1 minus x2, which can be taken uh, in a vector form in matrix. Assume the starting point of P naught as 8, 2, we will be, which will be shown in next slide. To calculate the value of gradient at this point, Vp naught equal to the f of P of 0, which will be equal to 7 plus 2 minus 2 into 8, and 4 plus 8 minus 2 into 2, which will be giving us minus 7 and 2, 8. And calculate unit vector pointing in this direction, we will be getting minus 0.659 and 0.753. As shown in the figure given below, uh, we have got various value for various points, which were in this feasible region below these line, under these line. That in the direction of Vp0, we will be violating constraint before the unconstrained optimum is reached. If we assume the constraint optimum lies at the corner point of the constraint set, which will be these corner sets, optimum lies at a corner point constraint set. All we have to do is project P0, Vp0 to the nearest constraint. With this is P0, 8, 2, the nearest constraint will be P1, P2 or P3. And we can move along that constraint to corner point, then go to another corner. Like first we go from P0 to P1, then P1 to P2, then P2 to P3. Then until an optimum is found. If the optimum is not a corner point, then there will be an iteration in our search. When the optimum search direction as projected along the constraint will reverse itself. If there is no further corner points, this will just go reverse and find another corner point. Then if it doesn't find another solution, it will reverse and find another point. If this happens, we will know that we have overshot the optimum, which is also known as overbiased, and that must search for it between most recent two corner points we have visited. That's all. Thank you for listening us.